Hello and welcome again to this online course on fundamentals of composites and cellular materials. So, in today's class my plan is to discuss on aramid and ceramic fibers, and in the ceramic fibers I want to concentrate on alumina in today's class. So, in the last few classes we were discussing about fibers, and then we talked about glass fiber, we talked about boron and carbon fibers in the last class. Okay. Now, I want to shift a little bit towards organic fibers, okay, or polymeric fibers. So far I have not discussed about polymer fiber at all. Okay. So, and we will be seeing that polymer fibers are used hugely in all kind of commercial applications, and then I will shift into ceramic fibers. Ceramic fibers shows extremely high temperature strength. So, we should talk about ceramic fibers as well. So, in today's class, in terms of ceramic fiber I will talk about alumina fiber, and then in the subsequent classes I will go into SiC fiber and other fibers. Okay. So, let us start on talking about organic fibers. Now, organic fibers are basically polymeric fibers. So, you have polymer material, and the idea here is to align the long chains in the axial direction and to make the fibers like that, so that you achieve quite or fairly high strength in modulus. Obviously, as you understand, polymers materials does not show very high modulus like 10 GPa, in the range of 10 GPa, right. Now, if you can align this polymeric chain properly, then you can have higher modulus. As you can see here, the data has been mentioned around 70 GPa. Obviously, I have mentioned about boron fiber in the last class. I have talked about glass fiber also, carbon fibers. Obviously, those fibers shows very high strength and modulus, but organic fibers definitely does not show that high strength and modulus. But then there are a lot of commercial applications where you do not really need that high strength and modulus, but you need some fibers which shows fairly high strength and modulus, and you can produce them easily without much of expenditure and much of problems. Okay. So, organic fibers comes into that that regime where fairly good strength and modulus can be achieved and without much sweating, okay, or without much expenditure. And these polymeric fibers or organic fibers are mostly crystalline in nature. Okay. So, I will talk about two organic fibers, that is polyethylene fiber and aramid fiber. These two fibers I have chosen because these are the mostly used organic fibers in the market. Okay. And I will concentrate on aramid fiber mostly in today's class. So, polyethylene fibers, or basically what we call it high molecular weight polyethylene fibers, these are again crystalline in nature mostly, and these are made by gel spinning. Okay. So, spinning method already we have discussed. So, gel spinning is one of the method by which fibers can be synthesized, and this ultra high molecular weight polyethylene is made basically or synthesized by gel spinning method, and it shows fairly high strength and modulus, but not like aramid fibers. Okay. However, the specific values are quite high. Okay. And the applications, as you can see here, mentioned to make protective vests in military applications. Okay. Riot shields, as you can see here, the riot shields have been shown here. Okay. This kind of vests also can be made. I mean the fibers which are used to reinforce this kind of vests are polyethylene fibers in most cases. Also Kevlar or aramid fiber is also used, and then ballistic armors and all those things, okay, are being used. These kind of polyethylene fibers are being used. But in today's class I would want to concentrate more on the aramid fiber. So, let us talk about aramid fiber. Now, from the name of aramid fiber you can see here, it basically a combination of aromatic and amide group. Okay. So, you can see here amide basically is CONH2 group. Yeah, this CONH2 group, this is the amide group, and let me change it to laser pointer. Yeah. So, the CONH2 group is the amide group, and then with that you attach aromatic rings and you get aramide structure. But then and you can see here actually that has been done here. So, CONH is residing between two aromatic rings, but then this combination, there will be multiple combinations by which you can have amide and aromatic groups attached. For example, you can have couple of amide groups together and then one aromatic come into picture, or two aromatics together and then one NH2 one amide group can come there. Okay. So, there could be multiple variations by which you can attach amide group and aromatic group, and all of them we do not call Kevlar or aramide fiber. Okay. By the way, Kevlar is the commercial name. There are other commercial names as well, okay, like Technora and other things, but basically it is aramide structure. Now, as I was talking about is that we do not call everything aramide fiber if there is amide group and aromatic group. So, what is the definition of aramide fiber? One thing has to be made sure is that at least 85% of these amide groups are attached in between two aromatic groups, then only we call it aramide fiber. You can see here it says that the Federal Trade Commission they have given a definition that a manufactured fiber in which the fiber forming substances is a long chain synthetic polyamide in which at least 80% of the amide group, that is CONH group or linkage, are attached directly between two aromatic rings. Okay. And obviously, why we are talking about aramide fiber? Because of high strength, modulus, very important factor, very extremely important factor. These are flame resistant, even if these are polymer material, but these are flame resistant, okay. Self extinguishing, does not melt, and low smoke emission. Okay. That is why these are used in this kind of military applications. Okay. Low coefficient of thermal expansion, good chemical resistance, yes, again a very important factor, and low electrical conductivity and low dielectric constant. Because of all these attributes, Kevlar fiber or aramide fibers are used in this kind of application, as I was showing earlier. Okay. So, let us go more into the processing of aramide fiber, and let us try to understand the atomic configuration or molecular configuration here. So, you have, again, if you look at this particular diagram, you have these amine groups, okay. We call it diamines attached with an aromatic ring. Similarly, this C is there, so COCl, this is basically acid halide group. So, we call it diacid halide, there are two chloride ions. So, diacid halide attached with again aromatic ring. So, again let me just say it once more, we have diamines and diacid halides, they react, and then you have this NH and then you have this CO, and then ultimately those gets combined and you get CONH. Okay. That is basically the amide group. So, from the amine and the acid halide you get this amide group, and this amide group is basically residing between two aromatic rings, okay. And that is how you get the aramide structure. Okay. So, if we look into the processing again in little bit more details. So, the first step is that you go for solution polycondensation of diamine and diacid halide. Let me just go back once more. So, this is the diamine and this is the diacid halide. These two compound or molecular structure goes through solution polycondensation, and that gives this particular aramide structure, and the reaction takes place at a low temperature, very low temperature in the range of 0 degree Celsius. Okay. So, and that leads to the formation of the aramide. So, now you have got the aramide. So, you get, after getting the aramide, that gets pulverized, that means you make it make it in powder form, and then you go for washing and drying, and then a very important step is mixing with concentrated H2SO4, 100% H2SO4, and I will discuss about this particular step in details. That is why it has to go through this particular step of mixing with 100% H2SO4, and then once that is done, then you go for a spinning method, which I have discussed earlier, dry jet wet spinning method at 100 degrees Celsius. Now, dry jet wet spinning method is basically a combination of dry spinning and wet spinning. Okay. I will discuss this again as we move on. Now, question here is that why do we need to go for this low temperature? Okay. This low temperature is extremely important to inhibit byproduct formation. What do we mean by byproduct formation? Again, if we look back, as I mentioned earlier, is that I want this polyamide, this amide group to be attached between two aromatic rings, and that should be around 85%. Okay. If there is something else happening, that we are calling as byproduct. Okay. So, yes, it has to be done at low temperature basically to inhibit byproduct formation, and another again very important factor is that to promote linear polyamide formation. Okay. We do not want any kind of cross linking to take place in this kind of, ideally speaking actually, that we should not be having any kind of cross linking or any kind of other kind of structure formation. It should be linear structure, okay, and that is why, because if you go for linear structure, then axially the strength is higher, modulus is higher. Okay. So, that is why the whole experiment or whole reaction is done at lower temperature. Now, let us concentrate on this mixing with 100% H2SO4. What exactly happens in that stage? What exactly happens? So, after this reaction here, this solution polycondensation of diamine and diacid halide, you get this polymeric chain of aramide. Okay. This is a random coil structure. Okay. Now, as it comes in contact with 100% H2SO4, it goes through certain kind of structural change. What happens? So, the first thing happens is that these random coils gets straightened out and it gives this kind of random rods. Okay. And again with time, these random rods gets aligned and they makes groups like this kind of liquid crystalline state. So, you can see here a number of random rods come together, come closer and makes this kind of zones, okay, of liquid crystalline zones. Okay. So, this kind of alignment takes place in presence of H2SO4, and finally, what happens with this regions is that ultimately you get this kind of nematic liquid crystal structure. What is nematic liquid crystal structure? Nematic means basically when you have aligned this kind of rods, however, this alignment is random. Okay, that is called nematic. So, obviously, there is some regular kind of alignment, that is called smectic. So, you can see here, I think the difference here is that in nematic is that the alignment is in a particular direction, true, but then the alignment of the rods are actually random, but here you can see they are actually in groups in case of smectic. So, in case of Kevlar or aramide, where you make this kind of liquid crystal, we are calling it as nematic liquid crystal, where the alignment is in a particular direction, however, these are not in groups. Okay. So, now once this thing is done, okay, now the process of dry jet wet spinning comes into picture. So, if you see here, this is the process of dry jet wet spinning method. So, you can see here this liquid crystalline state is there, the domains are there. These are all nematic liquid crystalline domains, and now these domains are pulled through this dry jet wet spinning method. So, you can see this is an air, there is an air gap at around 4 centimeter, 1 to 4 centimeter, and this air gap, through this air gap some evaporation takes place of the solvent. Okay, so that's why it is required. So, this is the dry spinning stage, and then there is a coagulation bath. Coagulation bath is nothing but basically it is again low temperature water is there. So, that basically washes off the extra H2SO4 which was being used earlier to go through these particular steps of from random coils to ultimately you get this liquid crystalline state. So, basically to wash off that extra high H2SO4, this coagulation bath is required, and that is the part of the wet spinning. So, you have dry spinning and wet spinning, and that ultimately leads to the formation of the aramide fiber, from aramide material to aramide fiber. I hope the process is clear to all of you. So, again we need to look into the properties, and depending upon what kind of Kevlar structure or aramide structure you get after the synthesis, you have varied properties, tensile strength and modulus. And another important factor here is that if you look at this thing, the tensile strain to fracture for K49 it is 2.8 and K29 it is 4. So, if I ask you which one should be used in case of making the ballistic vests. Okay. For example, K29 and K49 we are comparing that. So, obviously, the modulus is higher in K49. Does that mean we should use that as the ballistic in reinforcing ballistic vest? We also have to look into the data of tensile strain to fracture. In this case, you can see the tensile strain to fracture is higher in K29. That means, before the fiber tears off or gets fractured, gets failed, it leads to more amount of tensile straining before fracture. Okay. So, obviously, K29 should be preferred in case of making ballistic vests, even it shows lower modulus, very important factor. Okay. So, that is all about Kevlar fibers or aramide fibers strength and modulus and properties. Okay. And as you can see here, it has been mentioned that aramide fibers are not suitable for application involving compressive forces, just because it does not show very high compressive strength. If you compare with tensile strength, the value is 1/8, it is quite low. Okay. And now, we should look into the applications as well. So, there are multiple applications, starting from bullet vests to driving gloves, in the boots, working boots, military helmet. So, you have to have the weight has to be very low. Okay. So, these are made of polymers, okay, which are basically reinforced with again Kevlar fiber or aramide fibers. Okay. Different kind of gloves. Okay. Bicycle tire, yes. Okay. In some bicycle tires, heavy duty bicycle tires, Kevlars are used for strengthening the tires. Kart tires, okay. Fireproof clothing, yes, because as I was mentioning earlier, Kevlar fiber, aramide fiber being a polymer, it is polymer, but still it does not catch fire, it does not evolve too much of smoke, it does not it acts, in fact it acts as fire extinguisher. Okay. So, that is why in case of making fireproof clothing, also aramide fibers are used. Again there are some more applications. This kind of honeycomb structures are used in aircrafts, for example, flooring and different kind of panels. This aramide fibers are used. So, Now, I have talked about aramide fiber or organic fibers, okay, as such. So far we have discussed about starting with glass fiber, then we talked about boron fiber, we talked about obviously carbon fiber, and now we discussed about what do you call polymeric fiber or organic fibers. Okay. Now, it is time to move into ceramic fibers. Now, ceramic fibers are different kind of ceramic fibers are there, like oxide fibers, non-oxide fibers. For oxide fibers you can see alumina, silica, mullite, zirconia. Similarly, non-oxide fibers mostly it is silicon carbide. Now, why do we prefer ceramic fibers? The single most important parameter or factor for which ceramic fibers are chosen are their high temperature strength. Okay. The other fibers which I have talked so far, for example, the organic fibers or glass fiber, they actually lose their mechanical properties at higher temperature. Not carbon fiber, but the other fibers which I have discussed so far, they lose their high temperature strength. Okay. So, we are looking about high temperature strength and extremely resistant to corrosive media, then we should talk about ceramic fibers. Okay. So, you can see here high strength, high modulus, high temperature capability, free from environmental attack. Okay. That is the attributes of ceramic fibers. Now, if we talk about synthesis of ceramic fibers, there are basically three basic techniques by which ceramic fiber is synthesized. Number one is CVD or chemical vapor deposition. That means, you will be having a substrate on which this ceramic material will be deposited in the form of fibers. That is called chemical vapor deposition. We already discussed about chemical vapor deposition when we were talking about synthesis of boron fiber. The next one is polymer pyrolysis. Now, what is polymer pyrolysis? Polymer pyrolysis means you need to think about a precursor which is having high molecular weight. Obviously, this is a polymeric precursor which is having high molecular weight and long chains, and it should contains certain elements. For example, let us say I am trying to make silicon carbide fiber, right. That means, it has to have silicon in that. It is a polymeric material, will be containing silicon and carbon is anyway there, and we have to do certain thing so that this silicon and carbon gets combined and we get silicon carbide, but we get rid of the rest of the elements, okay, by a pyrolysis technique or higher temperature synthesis technique, which is called polymer pyrolysis. So, a precursor is polymeric long chains containing certain elements. These certain elements combine and give you the fiber material, but the other elements which are not required, they gets removed by the pyrolysis technique. And the last one is obviously the old age technique of sol gel technique. That means, basically you go through a process of making sol and then gel, and then ultimately you go for calcination to get the fiber material. Okay. In this you can see here the different fiber material. For example, here you can see Nextel 720 fiber. Basically, it is a combination of alumina and silica material, and here you can see again here is another fiber which has 70 Si 30C, and then the other trace elements are there. So, anyway, so now let us talk about synthesis of ceramic fibers. We will now talk about, we will take particular example of fibers like alumina fiber, and we will talk about that. I already have mentioned about polymer pyrolysis. What is polymer pyrolysis? The pyrolysis route of processing ceramic fibers with polymer containing silicon, carbon, nitrogen and boron, with the end products being silicon carbide, silicon nitride, boron carbide, boron nitride, different kind of, you can see here. So, the polymer chain has to contain, let us say you want to make boron nitride fiber. So, the polymeric chain has to contain boron and nitrogen, and your aim has to be make this BN structure by the pyrolysis method. Similarly, if you want to make Si3N4, then it should contain silicon and nitrogen atoms, and ultimately at the end it will form Si3N4. Okay. And sol gel technique also already I have mentioned is that it is the important factor here is that it is used to produce variety of commercial oxide fiber. So, one thing we have to keep in mind that in case of sol gel technique you can make only oxide fibers. Okay. So, the precursor material here is alkoxide. Alkoxide means what? You can see here MOR whole N to MOR. That means what is alkoxide? So, let me give you a very simple example of what is alkoxide. So, let us say we all know this equation or this reaction, let us say CH3OH, and then let it get reacted with NaCl. So, what do you get? You get CH3ONa plus HCl. Okay. Now, this CH3ONa, as you can see here, is basically this is R, this is R, and then you have O, and then you have Na means M. So, this ROM structure is the alkoxide structure. So, in case of sol gel technique, the precursor material is some form of alkoxide, and I will discuss in a few minutes that how this alkoxide leads to formation of MOM. So, you can see here this is the oxide you are making. Okay. So, let us move into the next one. Sol gel technique, as I was mentioning earlier, is a process in which it is used for fabrication of metal and ceramic oxide, and it involves conversion of monomers into colloidal solution, which we are calling sol. So, the precursor material in earlier case I mentioned about MOR, which is basically an alkoxide, okay, and this alkoxide, so you choose a certain solvent in which the alkoxide is dissolved to make a colloidal solution, and this colloidal solution goes through this hydrolysis and polycondensation method or reaction. I will show you again, and that forms a network of gel. Okay. Gel is basically a viscous material, and then this gel, once you get this gel, you make fiber out of this gel. Okay. Remember, this gel is yet to form the oxide, it is not the oxide. Okay. So, it is a gel, and this gel goes through a calcination process of aging, drying or thermal decomposition, and that ultimately leads to formation of the oxide. Okay. For example, you can see here in this particular case, this is MOR, okay, and this you go through a hydrolysis process. So, you get MOH and ROH, okay, and this MOH, two MOH molecules ultimately will give you MOM and H2O, and that is water condensation method. Similarly, you can think about so this once you get this MOH, so you take this MOH and it also can react with this MOH is there. So, the first material is MOR, so that can react with MOR as well, and then that can give you MOM. So, you have MOM and ROH, and that is called alcohol condensation. Okay. So, it could be water condensation or alcohol condensation, okay, but the final product is MOM or an oxide. Okay. And that is how by sol gel technique also you can think about getting ceramic fibers. So, to just recapitulate, I am just trying to say it once more. So, first you make a sol of alkoxide, using a particular solvent, and then that salt goes through hydrolysis and polycondensation, and then it forms a network of gel, and that gel is made into fiber, and this fiber now goes through the process of calcination, and that leads to formation of the oxide fiber. Okay. And the first one I want to discuss here is the alumina fiber. So, in case of alumina fiber, alumina has several different allotropes like eta, gamma, okay, and all those and alpha and other things. And in that case, alpha is the most stable form, and it also shows fairly good mechanical properties compared to the other allotropes. So, the idea here is to make alpha alumina when you try to make alumina fiber. Now, the starting material here is this boric salt of aluminium. So, that is the alkoxide here, the precursor material, and this precursor material it can decompose at high temperature by the process of Sol-Gel technique, and it gives you this eta Al2O3. Obviously, you do not want to stop there. So, you go for heat treatment to get alpha Al2O3, right. And then in this process from eta Al2O3 alpha Al2O3, if you are doing heat treatment you get alpha Al2O3, but the basic problem in this case is that the process of eta to alpha is a very slow process, and that leads to increase in grain size, and in terms it leads to deterioration in the mechanical property or lower mechanical properties. Okay. So, how do you get rid of this? The idea here is to this slow nucleation process has to be changed to a faster nucleation process, and what can be done for that? Okay. Then a process modification agent could be used, or a nucleating agent could be used. Okay. For example, iron oxide. Okay. So, Fe2O3, a nucleating agent hydrous Fe2O3 could be used, and that will enhance the nucleation process. Now, the question could come in your mind, why Fe2O3? Actually, Fe2O3 is almost similar structure, or we call it isostructural to Al2O3, and that is why it acts as a perfect nucleating agent for Al2O3, and the nucleation process, the kinetics of nucleation process gets enhanced, and you get very fine get a very fine Al2O3 in the process. Okay. Depending upon how much of oxide iron oxide you used, you can see here the temperature from 10 degrees Celsius to 977 degrees. So, there is a decrease in temperature also takes place in the process. Okay. So, that is the basic technique of alumina fiber synthesis, where you start with a boric salt, and then you get eta Al2O3, and then you go for heat treatment to get alpha Al2O3, and during that you use a nucleating agent either Fe2O3 or SiO2, and then ultimately you get very fine grains of Al2O3 in the process. Similarly, again by adapting the Sol-Gel technique, you can get mixed oxide fiber as well. Okay. So, you can start with again this organoalumina compound with silicates, and you go to Sol-Gel technique, and ultimately ultimately get a mixed fiber of alumina and SiO2. There are multiple examples of by which you can make alumina fibers. For example, in this case the precursors are aluminum nitrate and malic acid, and again that goes through the technique, the steps of Sol-Gel. So, you go for gel making, okay, and then spinning is done, okay, to get the gel fiber or precursor solution, and then it goes through a condensation, and ultimately here it is actually getting hand drawn, okay, to get the precursor fibers, and then drying and sintering, which are calling as calcination, you get alumina fiber. And depending upon what is the calcination temperature, you can see here there are different temperatures like 800, 1000 and 1200 degrees Celsius, and you can see from gamma to alpha, ultimately at higher temperature of calcination you get better structure of alpha alumina. Okay. So, there are multiple examples, multiple routes, multiple precursors by which you can get alumina fiber, but the basic step or basic process is mostly similar, is that you go through some kind of sol-gel technique by which you get these oxide fibers. Okay. Now, looking back into the properties, you can see you can have alumina silica fibers, that is mixed fiber, or you can have also alpha alumina, and you can see there are different companies, they have different names, commercial names, from Altex to Nextel. So, there are different series of Nextel fibers made by 3M company. Similarly, Sumitomo, they have made different kind of alumina fibers as well. And then what you see here, the basic point to take from here is that it has very high tensile strength. Okay. 2 GPa, in the range of 2 GPa, 3.5 GPa, so quite high tensile strength, and modulus is also in the range of 200 to 400 GPa, okay, depending upon what is the ultimate final product. So, again you can achieve very high strength, high modulus, and wide range of properties. And you can see here how alumina fiber looks like. Okay. Yeah, a spool you can see here, Nextel 440 spool, continuous alumina fiber, and applications as you can see in ball valves, in piston pumps, in insulation materials for nuclear reactors and space shuttle. So, exotic application again. Okay. So again the application of alumina fiber or alumina silica fiber is high temperature application and where you need high strength and high modulus. So, ultimately I come to the conclusion of today's class. So, I started talking about organic fiber. In the organic fiber, I talked about two different fibers. One is polyethylene fiber, other one is aramid fiber. As I mentioned, polyethylene fiber is made by gel spinning. On the other hand, aramid fiber is made by a unique technique called dry jet wet spinning method. And the advantage of these fibers, especially the aramid fiber, is that it shows very high, fairly high strength and modulus, and it does not catch fire, it does not in fact it acts as fire extinguisher. Okay. So, that is why these are used in military applications, in fire fighting applications. Okay. Then we talked about ceramic fibers. So, initially we talked about the basic fabrication techniques of ceramic fiber. There are three techniques as I mentioned earlier. The first one is polymer pyrolysis, second one is sol gel, and third one is chemical vapor deposition. So, we have talked about sol gel. In the next few classes, we will talk about CVD method and polymer pyrolysis by which these ceramic fibers are being synthesized. Okay. And we talked about alumina fiber in today's class, which is basically made by or generally made by sol gel technique. So, in the next class, my plan is to talk about some more ceramic fibers like silicon fibers and whiskers of silicon carbide, and how they are synthesized, what are their properties, applications, those few things I want to concentrate in the next class. So, with that again I thank you all for lending your ears, and I meet you in the next class. Thank you all.